All right, let's get into it. Today, we're going to take you on a pretty wild ride through 4 billion years of history to answer one giant question. How did our planet go from a dead, molten rock to a world absolutely teeming with life? So let's just jump right in. This is the big one, right? The question that kicks off our entire journey. And it all starts not with a gentle spark, but with incredible cosmic violence and a chance collision that, believe it or not, changed everything. To get this story started, we have to go way, way back to the very beginning. We're talking about an era of constant collisions and heat you can't even imagine. This is where the stage for life was first set, literally forged in the chaos of the early solar system. The first 100 million years were just an absolute frenzy. It all kicked off when a nearby galaxy slammed into the Milky Way, which triggered the birth of our sun. Then, these planetesimals, basically the building blocks of planets, started crashing into each other. In just 10 million years, our Earth formed, but it wasn't alone. It had a twin, a Mars-sized planet named Theia, stuck in the same orbit. You can probably guess what happened next. A catastrophic, inevitable collision was coming. And that one single cataclysmic event, well, it was everything. The debris that got blasted into space from that massive impact eventually clumped together to form our moon. And as the moon started to drift away from Earth, it began to tame our wild, spinning planet. The moon's gravity created this incredible chain reaction. It basically acted like a brake, slowing down Earth's frantic spin. And that cooldown period was absolutely crucial. It let the molten ocean of magma finally cool and harden into a crust. It also allowed all that steam in our early atmosphere to condense and rain down, forming the very first oceans. Okay, so with the planet finally calming down, with oceans and an atmosphere, the stage was now set for maybe the most improbable event of all: the origin of life itself. Now, this wasn't some single lightning strike. It was more like a cosmic recipe unfolding, step by step, in Earth's primordial kitchen. First, you've got your ingredients, amino acids, delivered fresh by comets. Then, deep underwater, these geysers started cooking those ingredients into the first strands of something called proto-RNA. The strong tides from our nearby moon created these wet, dry cycles that linked those simple molecules into long, complex chains. And finally, fatty membranes formed around them, creating these tiny, protected bubbles, the first pre-cells. The invention of the ribozyme was a complete and total game changer. I mean, think about it. For the first time ever, information could be stored, it could be copied, and, here's the key, it could change through copying errors. This was the moment natural selection finally got its engine. Life was no longer just a chemical reaction. It was information that could evolve. But RNA, well, it's kind of flimsy. For life to really take off, it needed a much safer way to store its genetic code. So life pulled off its first major software upgrade. It switched from that fragile single-stranded RNA to the robust, double-stranded DNA helix we all know. This created a secure, long-term library for all its genetic information. So life's got its stable code. It's ready for the next big thing. And this next act? It was an innovation that was going to poison the entire planet for most of the life that existed and completely remake the world. Here's the problem. After hundreds of millions of years, the easy-to-get chemical food in the oceans started running out. Life was facing a major food crisis. So, some microbes, these things called cyanobacteria, developed a new superpower: photosynthesis. They figured out how to eat sunlight. But this amazing trick came with a dramatic, unintended consequence: a toxic waste product called oxygen. This event, which we call the Great Oxidation Event, was life's first attempt at global engineering. The new oxygen first reacted with all the iron in the oceans, causing it to literally rust and sink to the bottom. That's what turned the seas from brown to blue. Then it filled the air, changing the sky. For almost all life on the planet at the time, this was a catastrophe, a poison that caused a mass extinction. But for a few others, it created an unbelievable opportunity. You'd think this would be a total disaster, right? But in the wake of this crisis, life didn't just survive. It actually evolved to use that very same oxygen that had been so deadly. And in the process, it became vastly more complex. The evolution of the eukaryotic cell, This was like upgrading from a tiny one-room hut to a massive factory with specialized apartments. You get a central nucleus to protect the precious DNA, and you get these new power plants, we call them mitochondria, that let the cell use oxygen to generate huge amounts of energy. This new design just paved the way for much, much bigger and more complex organisms. And get this whole idea of going from one cell to many, what we call multicellularity, it wasn't some one-off fluke. It evolved independently in these new eukaryotic cells at least 25 different times. That just shows you what a winning strategy it was. Once cells had all this new energy and structure, teaming up was just the next logical step. But just when life was getting all sophisticated, the planet threw another massive curveball, a series of extreme, global ice ages known as Snowball Earth. We think they were triggered by cosmic rays from nearby supernova. The entire planet froze solid, from the poles all the way to the equator. So where did life go? It hid. It found refuge in the dark, cold waters deep under the ice. And just like the oxygen crisis, these insane pressures didn't stop life. They actually accelerated its evolution. These incredibly stressful times forced life to become tougher, more cooperative, and way more innovative. So after surviving both fire and ice, life emerges from that final deep freeze into a world that was finally ready for the main event, the arrival of big, complex animals. All the key ingredients were now in place. Atmospheric oxygen jumped up to a level that was high enough to support active animals. Sea levels dropped, exposing more land, which meant more rivers were washing crucial nutrients like phosphorus into the oceans. The world's seas were basically primed for an explosion of complexity. And this is where things get, well, really weird. It led to the first large visible life forms, the strange and mysterious Ediacaran fauna. These were bizarre, soft-bodied creatures, some over a meter long, that looked like nothing on Earth today. You can think of them like a first draft of large-scale life, an experiment in how to build a big body. But then, another extinction event came along and wiped the slate clean of most of these early experiments. This wasn't a step back, though. It actually spurred the evolution of a brand new toolkit, hard parts. With more calcium available in the oceans, organisms started building skeletons and shells for protection and for support. So that's where we leave things, right on the very cusp of a revolution. The world is rich with oxygen, the oceans are full of nutrients, and life has just invented the blueprint for building complex animals. The stage is set, all the pieces are in place, which leaves us with one final, tantalizing question that's going to kick off the next great chapter in the story of life.